This lecture here is going to be on size and scale of planets. We're really going to be defining what big and small are. Remember, they're relative. That something really big compared to something else could actually be really small. So when comparing it, you have to make sure you have reference as to what it is we're looking at. So inner planets are small compared to outer planets. But planets are small compared to a solar system. And solar systems are almost infantile compared to a galaxy and so on. So if you have a chance, be sure to watch this video here. The video here is on powers of 10. I kind of talk you through it, and we watched it in class. Make sure you get a chance of taking a look at what big and what really small actually are. Which brings us to lab activity 2 in the binder, comparing planets. We're going to be able to do our calculations first before we actually draw the radius using a compass. So if we could determine the radius by dividing the diameter by 2, so we're going to use table 12-1. We're going to scale them. We're going to use 1 millimeter to equal 1,000 kilometers of that respective planet to determine the scale model, the radius of the planet we're solving for. For example, in 12-1, you'll find that the diameter of Mercury is 4,854 kilometers. Divide that by 2, I find it's 2,427 kilometers of a radius. I divide 2,427 kilometers by 1,000 to get it converted into millimeters, and you find that it's 2.43 millimeters. So we'll just write it as 2.4 millimeters because 0.03 millimeters would be really hard for you to determine. So that's how we start this off. So I'll do a couple more with you. Venus. Venus has a diameter. I divide it by 2. I find that its radius is 6,056 kilometers. Divided by 1,000, I would find that it's 6.1 millimeters. So I could put 6.1 millimeters here. The Earth has a diameter. I divide it by 2. I find that its radius is 6,376 kilometers. Divided by 1,000, it's 6.4 millimeters. And so on. So you can go ahead and complete the remaining planet scales in your binder. Now moving on to lab activity 3, rotation and revolution. We're looking at speeds here. So before we begin solving, we're still sticking with the idea of AUs, but this isn't listed in AUs. These are actually listed in millions of kilometers and billions of kilometers. So we're actually putting a number to them. So diameters, I kind of rounded it off numbers to just for you to work from. Radius is going to be half of those. You're solving for Venus, Jupiter, Saturn, and Pluto. And circumference, and this is where we've come to. Circumference is going to equal 2 times pi times r. Well, you can also see that the circumference of the distance is the distance around a spherical body. In general, it's the equator of that spherical body we're measuring. So 2 pi r is the same thing as pi times diameter, since diameter is just 2r. So either way you want to solve, it's fine. So within lab activity 3, we also solve for angular speed and linear speed if we are on the planet. So the rotation, what the speed would be if we were standing at the equator of a planet. So angular speed, that's the rate at which an object rotates or revolves, and it's measured in rotations per minute and rotations per second. And it can also be measured in meters per second. So for linear speed, we're actually going to take 2 pi r divided by time for one rotation, which is circumference divided by time. So here we can start off with, let's measure for RPM. So I did an example for you on Earth. So imagine Earth with me for a second. To solve this, I know it rotates once in 24 hours. But I'm solving it for rotations per minute. So I need to find how many minutes are in 24 hours. So 24 hours. So notice I have parentheses here. 24 hours over 1 times 60 minutes per hour. I find that one rotation divided by the quantity here is 0.0007 RPMs. To solve rotations per second, I take the same concept. I'm still solving for Earth. One rotation, 24 hours over 1. Notice my parentheses here. So order of operations, make sure you do it in the proper order. 24 over 1 times 60 minutes per hour times 60 seconds per minute is my denominator. I get 0.000012, and that's my answer up here. And you can go on and solve for the linear speed for the Earth. So you're going to use this model. So linear speed, I'm going to do it for Mercury. How do we come up with 3 meters per second? Well, we take the circumference divided by time. So circumference is going to be 2 pi r, and we're going to make sure that our final units are in meters per second. So here's how I do it. Given on one of the pages before, it's solved or shown as the circumference here is going to be 15,400 kilometers, but I want it in meters, so I got to multiply my numerator times 1,000 meters per kilometer. That said, now I divide it by the quantity of how long does it take in seconds to make one rotation. Well, 59 days of a rotation times 24 hours in a day times 3,600 seconds per hour. I simply took 60 minutes times 60 seconds. So I found seconds in an hour. So numerator divided by denominator solves for me, or tells me it's linear speed. If I'm standing at the equator of Mercury, I'm traveling at 3 meters per second. And you can go ahead and solve for Mars, Jupiter, and Pluto. The angular speed in RPMs, RPS, and be sure to solve for linear speed for the missing Earth, Mars, Jupiter, and Pluto. And the other ones, answers are provided. So make sure you know the process here. So here's a new part of Lab Activity 3. We will be solving these. We'll do these in class. The orbital velocity of planets. The orbital velocity is going to equal the square root of g, it's a gravitational constant, times m, the mass of the body, divided by r is the radius of the distance to the center of mass of the object orbiting, to the center mass of the object that it's, so the orbiting body to the center mass of the object in which it's orbiting. So how fast is a planet moving around an object in which it orbits, or revolves? So remember that 1 Newton is 1 kilogram meter per second squared. You should have learned that in physics. So in example problem 1, the satellite is being sent into space for remote sensing. Calculate the orbital velocity necessary so the satellite orbits the Earth. So g is the universal gravitational constant. It's going to be the same for both problem 1, problem 2, any problem. The mass of the Earth, 5.98 times 10 to the 24th kilograms. And r is the distance to the center of the Earth, is 6.57 times 10 to the 6 meters. Now, here's the math. Here's how it sets up. And it's 7.9 kilometers per second, or 7.9 times 10 to the 3rd meters per second. And example problem 2 is a satellite being sent into space to study Jupiter. Calculate the orbital velocity necessary so the satellite orbits Jupiter at 71,500 kilometers. So, that said, you can take a look at the numbers how I set it up, solve it, make sure you know how to set these, program these into your calculator. Next problem, finding weight on other planets. If you calculate your weight, if you know your weight on Earth, you can calculate your weight on other planets. You must recognize that mass is constant. Weight is what changes. Weight is based on the relationship of two masses at a distance. I weigh about 195 pounds. My mass is 88.6 kilograms. My mass is 88.6 kilograms everywhere in the universe, even though my weight changes, which is based on the gravitational field. So you will need to solve using a ratio, where 1 kilogram weighs 2.2 pounds on Earth. 1 kilogram also weighs 9.8 newtons on Earth. So divide your weight, take your weight in pounds, and divide it by 2.2 pounds per kilogram to find your mass in kilograms. And that's how I took 195 divided by 2.2 is my ratio to find my mass in kilograms. So weight in pounds, you can use a classroom scale if you know your weight. Mass, you find by dividing your weight in pounds by 2.2 pounds per kilogram. That's a conversion. Weight in newtons is F of g is weight equals mass times gravity, where F of g is weight and m is mass and g is acceleration due to gravity. And on Earth, that's 9.8 meters per second squared on Earth. So 1 kilogram mass weighs 9.8 newtons on Earth. 1 kilogram times 9.8 meters per second squared is 9.8 newtons. So we're solving the table down here. So if I know my mass, it's constant. So your mass is going to be constant everywhere. So I can solve for, and I want you to see this ratio here. This is a ratio to solve for your weight in pounds with a different g. So your weight in pounds on, say, Mercury, I would set this up. I want to use a ratio. I know on Earth, I weigh 195 pounds. So you would insert your weight on g of 9.8 meters per second squared. That's going to equal x, that's what you're solving for, over g on that planet. So where it's a much smaller acceleration due to gravity, you're going to have a much lower weight, which I just called 72 pounds here. It's actually kind of ironic because when I go on a diet and try to lose weight, I just go weigh myself on a different planet with a lower g. Anyway, poor humor. Yes, I know. Last but not least, let's see if you can solve this complex problem. There's a whole lot going on here. Let's see how good you are. An astronaut on Earth, a weight of 160 pounds, travels to a newly found distant planet that is 25 AU from Earth. She travels at 95% of the speed of light. The planet which she arrives at has a surface gravity of 15.5 meters per second squared. The planet's diameter is 80,000 kilometers, and it takes 2.5 Earth days in which to rotate. Solve the following. Check those out. Try to solve them. We'll go over them in class.